Hello and welcome to this Electrical Science and Principles training video. In this video we're going to answer question 6 of the 8202 Level 3 written answer exam from April 2022. All the information here is freely and readily available from the website, so we're not giving away answers to future exams, we're just going over answers from old ones for those people who want to know what they should have put for the answer. Thanks to so many people for chipping into the channel. Big thanks to Mark Adamson, Linda and Dee Dee for buying me coffees, it's very much appreciated. And further thanks to SK, I think that's your name, C Inglis and Luke Giles for chipping in via super thanks. I really do appreciate each and every expression of appreciation, so thank you for that. Okay, so on to the question for this video. It goes as follows. A 0.28 Henry inductor has a resistance of 80 ohms and is connected in series with a capacitor of 38 microfarads. They are connected to an AC 230 volt supply at 50 Hertz. Calculate the circuit current. Now, if you don't understand any of the steps we're going to follow here, please go and check out my AC theory playlist as it explains all the different elements that we're going to use. So let's get stuck into the question now. Okay, so I've written the question on the board there so that we've got it clearly in mind as we go through this answer. And I've gone to the trouble of creating the circuit diagram that this question is telling us about. I think this is a really important thing to do, even just to help yourself. The question doesn't ask you to draw the circuit, but I always like to draw it out just so I can keep in mind what it is that I'm actually dealing with. So we've got a series circuit and we've got a 0.28 inductor with a resistance of 80 ohms. So what I've done is I've taken that inductor and I've kind of broken it down into its component parts. So we've got here the inductive part of that represented by this coil, and then we've got the resistance of the coil separated out as an individual component. Now, if we were talking about a literal coil here, a literal inductor, these wouldn't be two separate parts. It would be one winding of copper, one coil of copper, and that one coil of copper would have an inductive part to it because it's a coil, and it would have a resistive part to it because it's made out of a copper wire, which has low resistance, but it has a certain amount of resistance anyway. And those things combined are what start to create things like power factor and other issues. But what we're going to do here is we're separating them out into their component parts because we need to do that in order to figure out what the current flow is going to be. So it's a good idea to draw the circuit, and then it's a good idea to sort of label it up with the relevant bits and bobs. So let's start that now. Okay, we'll make the resistor. We know that that has a resistance of 80 ohms, and it's also a good idea with this kind of question to just sort of list the things that the question gives you and then try and figure out what the question is trying to ask you for. So that can sometimes help you to call back to mind certain formulas that you need. So we'll write down underneath here just the list of all the things that we know about this circuit. Okay, and again, there's no marks for doing all of this. This is just to kind of gather all your information and make sure that you're ready to go. This is how I used to answer exam questions myself. It's how I used to teach my learners to answer exam questions, and I think it's a pretty valid way of going about this. So looking at the inductive part here, that has an inductance of 0.28 henries. So of course the symbol for that is L for inductance. That's not the most obvious one in the world, but that's what it is. L is equal to 0.28 henries. So we'll put that on our list of stuff that we know. Put that down there. And what else do we know about this circuit? It's in series with a capacitor of 38 microfarads. So let's put that on as well. So the capacitor is 38 microfarads. So we put down C is equal to 38 microfarads. Now, at this point, you can see here that we're dealing with whole units of ohms, we're dealing with whole units of henries, but here we've got a submultiple of farads. So that little Greek letter mu indicates micro. So when I write that down here, I'm going to write that in two different ways. So C is equal to 38 microfarads, 38 microfarads, which can also be written as, so I'm going to write this down in a slightly different way to remind myself to do this when I do the calculation, otherwise I'll get the wrong answer. You can write that as 38 times 10 to the minus 6 farads. So do you see there what I've done is I've just swapped that micro symbol, I've swapped that out for times 10 to the minus 6, and a little bit later in the video when I do the calculation I'll show you the easy way of putting that into your calculator. There is a list of multiples and submultiples that we need to learn, that we need to know, but we'll cover that in a different video. This is kind of the recapping stage, so hopefully by this point you're well familiar with how this works. What else do we know about this circuit? They're connected to an AC supply at 50 Hertz. So we know we've got that connected to a supply here of 50 Hertz. So we know that the frequency, lowercase f, is equal to 50 Hertz. And the final part of the puzzle, which is something that I've actually missed out of the question when I wrote it up here because I wasn't paying full attention, is that we've got an AC circuit of 230 volts like that. So we can put that in down here. So we're going to say that the voltage of this circuit V is equal to 230 volts. So let's just get both of those added to our list of stuff we know. We know that the frequency is equal to 50 Hertz, and we also know that the voltage is equal to 230 volts. So it's a bit like when you're cooking, you sort of want to get all your ingredients together before you start, so you're not dashing around the kitchen trying to find things. Down here we've got all of our ingredients for this question, and what we want to know is, what are we cooking? Okay, so what's the final outcome of this going to be? We want to find the circuit current. So the final part of this is we want to know how much current is flowing into the circuit. So how much current is there flowing into the circuit? That is the goal. That is what we don't know yet. So we're going to try and figure out how to find that answer. Okay, so when we start looking at this question, we might be thinking, right, I, that's what I need to find. So you start thinking about formulas that involve I and some of the information that you've got down here. So we want to know the current. Perhaps we're thinking Ohm's law might come straight to our mind. So we're thinking, right, I equals V over R. So we've got a V and we've got an R, that's great. But what that doesn't tell us is the circuit as a total. If you remember from other videos, we know that the voltage across here will be different across the different loads because it's a series circuit. We don't know the voltage across the individual components. We only know the total voltage being applied to the circuit. And so we've got to try and figure out a different way of finding the current. It does involve Ohm's law. We are going to use Ohm's law, but it's not kind of the first thing that we can leap to, because actually we're missing some other information. If we want to use Ohm's law in this case, we don't need to know just the resistance of the circuit, because we know the resistance of part of the circuit. We need to know the impedance of the circuit. Now, to find the impedance of the circuit, which is the total opposition to current flow in an AC circuit, so you can kind of think of it as the live resistance, I used to sometimes call it. It's a little bit misleading, that, but it kind of just connects those dots together. We're looking for the total opposition to current flow of this circuit, which is the impedance. To find the impedance, we need to know what the resistance, the inductive reactance, and the inductive capacitance of the circuit is. So to do that, we need to start diving into these figures. You're starting to understand why this question is worth 5 marks, okay, because this is quite a big question that'll take a little while. In reality, however long this video ends up being, you could probably answer this question in like a quarter or a third of the time. I'm just going through this quite slowly, step by step, to help you understand what's going on. So the first step along the way, if we want to find the impedance, is we need to find the resistance of the circuit. Well, we know that, so that's good. The next step is to try and find the inductive reactance. Now, finding the inductive reactance in this question will get you 1 mark, which is pretty cool. So let's try and figure out how to do that. Probably going to step off camera for a couple of minutes while I write this on the board, so you might not be able to see me. So let's have a look at this. So we're trying to find the inductive reactance to start with. So this is the first step. So we'll call this step 1. XL, you may remember, is equal to 2 times pi times F times L, like that. XL is equal to 2 pi FL. And then all we've got to do for this question is swap out the numbers that we've got. So again, think about our cooking analogy. Here's a couple of ingredients that we don't know in this equation. However, we're going to go back down here and you can find those. So we've got F and we've got L. So we've got the frequency and we've got the inductance. So we can put those into this question. So 2 times pi is just a constant, so that stays the same. We times it by the frequency of the circuit, which is 50. And then we times it by the inductance of the circuit, which is 0.28 henries. 0.28. Okay, so we'll head over to calculator cam and put that into the calculator. So we've got the calculator on. So we've got 2 times, and then to bring up pi on this one, shift pi, times F times the frequency, which is 50, times by L, which in this case is 0.28. And when we put that in the calculator, hopefully you can see there's a little reflection of the light there. I'll just lift it up so you can see. You can see there we've got 28 pi. Okay, so that's super helpful. Yeah, thank you calculator for giving me a number that I can't use. So 28 pi. So if we press this little button here, the SD button, you can see that's going to come out at 87.96. Okay, we could keep going, round that off further, but 2 decimal points is a reasonable value to round this off to if the question hasn't given you that. The reason that it's reasonable is that the highest level of accuracy we've got here is 2 decimal points. So there's no point rounding this off to more than 2 decimal points because it doesn't really give us any more accuracy than that. So 87.96 ohms is the answer to that first part. 87.96 ohms. Okay, hopefully we can still see that in shot. 87.96 ohms. So we've got the inductive reactance now, and that is worth 1 mark. So that whole bit there is worth 1 mark. Okay, so just a couple of points on the marking guide and the marking criteria here. The marking criteria says you can have a maximum of 1 mark only where basic recall of formula without values. So again, it kind of depends on how your assessor interprets that. But basically, for each part of this, if you're getting the formula for most of them, if you're kind of getting to the point where you're like, right, I know it's something to do with this, but I don't know where to go from there, then that's worth 1 mark. You'll get a point for that, which is pretty cool, really, to be able to just kind of scrape some marks out of this if perhaps you're struggling to answer the question, because it is quite a difficult question, to be fair. And it also says you can have a maximum of 2 marks for basic recall of formula with some values entered or incorrect answers given. So if you've managed to kind of think, oh, okay, I know that the F is 50, I know that that's 50 hertz, and sort of other bits and bobs as you're going through this, then you can again start to scrape some marks from this question. And it concludes by saying only reduce marks by 1 overall if an error is carried over, but subsequent results reflect the error correctly. So let's say I'd put the wrong value in here for some reason, if I'd misunderstood that to be, I don't know, if I'd put 38 in there or something, or 0.38 or something like that, and got the wrong answer for this part. If I took that wrong answer and used it in the next stages of this, so I'm still getting the wrong answer out of all of this because my initial numbers are wrong. But if the calculation I do is correct, so if the numbers on the calculator, if I've recorded that correctly, even though I've put the wrong numbers in, then you can still get some marks for that. Okay, so in that case, you could get right through this, get to the end, get completely the wrong answer, but the right process, and then you would lose a mark because you'd got the right process but the wrong final answer because you'd gone wrong somewhere along the way. So, you know, even if you're not 100% sure of how to do an exam question, if you're struggling a little bit, it's still a good idea just to have a crack at it, because your assessor might go through it and go, okay, well, you know, there's a mark there for a formula that's correct, or something like that. Obviously, it'd be devastating if you went wrong at this stage and every single following bit of this was wrong, if you know the process, but you get the answer right. But you could still scrape some marks from that and get yourself to a pass. Obviously, you know, we're not just about passing exams. We've never been about that. I'm not about that. But, you know, when it comes to the crunch, you know, you want to understand this brilliantly. You want to understand it really well, but you also want to pass your exam. So, you know, let's be realistic about that. Okay, so let's go through the next part of this, which is to find the value for capacitive reactance now. So we've got the inductive reactance, and now we're going to find the capacitive reactance. And again, if you have no idea why I'm going down this road, it might be a good idea to go back and watch that AC theory playlist, because it'll help you to understand this. But hopefully it will become clear why we're doing this in a moment. So let's try and find the capacitive reactance. So we're going to do that. XC is equal to, now this next formula is a little bit like this one, but it's a little bit different. We say 1 over 2 pi f, so we've kind of got that bit in there, but of course this is capacitive reactance, so we're going to find that the C goes there, 1 over 2 pi fc. Now when we write this bit in, this is where we've got to be a little bit careful where we start putting the numbers in. So we've got 1 over, and I'm not doing that line long enough because that's a terrible habit of mine, 2 times pi, so we've still got that same bit starting off with that constant. F is still 50 because that's still the frequency. But now we're going to times it by this value here of C. But remember what we said down here, that that's the value of capacitance with the submultiple on. And what we need to do is we need to put in the actual value, and I'll show you how to do that on the calculator now. So we put that in here as 38 times 10 to the minus 6. Okay, so we've just brought that figure, which is exactly the same amount of that, just expressed in a different way. So those two numbers represent the exact same amount, just expressed differently. We've brought that value up to here to put into our calculation. Okay, so we'll volley that into the calculator. and see what that comes out as. Okay, so we'll scrap that last bit. Now, the way I like to put this in here, I like to use the fraction button. So we press the fraction button, and then we go 1 at the top, move the cursor down, and then we've got 1 over 2 times shift pi times 50 again, and this time we're going to times it by 38, and then you see here times 10 to the x. So what you don't want to do here is do times 10 and then press the power button. You just want to use this button down here, and this is why, one of the reasons why I recommend the Casio FX85 GTX, the forebear of this. The 85 GT Plus, the 83 GT Plus, or the other version of this without the solar panel, which is the 83 GTX, all have this little times 10 to the X button here, which is super helpful. So you just press that, and then the next number you put in is the power, so -6 like that. So that's not taking 6 away from this bottom line, it's raising that times 10 to the power of -6. Again, hit equals, and you can see there that we've come out with an answer of 83.76575, so on and so forth. We'll stick to our 2 decimal places, so we've got 83.76, but looking at the number after the second decimal place, that's 5 or above, so that becomes the next number up, so that's 83.77. So we'll volley that into our process here, and you can see those 2 numbers are fairly close. Doesn't have to be that way, but the assessor's done that to kind of make life a little bit easier in a moment. Okay, so the next stage of this is to use these values to find the impedance. Now, if this was me, I'd go straight into the next big stage of this, okay? However, the way that the marking criteria is put together, you get a mark for showing an extra stage here, okay? So I'm going to show that extra stage now. That extra stage is to find the difference between the inductive reactance and the capacitive reactance. So that's what we're going to do. So here's step 3, and here's our third mark. Now, it's interesting at this stage, actually, it doesn't matter which way round we subtract this, okay, because what we're going to do in a moment is we're going to square this number. So even if we get a negative value out of this, we would still squaring that number takes that negative away, it cancels it out. But to keep life easy, I'm going to do the biggest number, take away the smallest number, because that's just the kind of the easy way of doing it. So we've got here, we'd do XL in this case minus XC. We could do this the other way around and it wouldn't make a difference as long as we put everything into the calculator right in the next stage. But just to keep it simple, we're going to find the difference between these. So what we're doing here is we're finding the total inductance of the circuit. So the inductive reactance and the capacitive reactance cancel each other out because they point in opposite directions in a series circuit. Again, more on that in another video. So we're going to find out the total reactance for the circuit here. So XL minus XC is equal to 87.96 minus 83.77. And that is going to give us, I should be able to do that quickly in my head, but I don't want to go wrong, so I'm not going to. I'm going to volley it into the calculator. 87.96 minus 83.77, and that gives us 4.19 ohms. Okay, so 4.19 ohms. So there is our total total reactance for this circuit. Okay, so that's our total reactance for the circuit, 4.19 ohms. Now, moving on to our next stage, we get to the point where we find the impedance. Okay, so to find the impedance, we use this formula. Okay, so this might look vaguely familiar to you if you did any maths at school, really. So we're going to say that Z is equal to, and again, I'd kind of show this in a couple of different stages. The marking criteria doesn't. I'd show this as Z squared is equal to R squared, so on and so forth. But what this is showing is Z is equal to the square root of R squared plus, and then we've got that difference between the two values of reactance that we found a moment ago. Okay, so R squared plus XL minus XC, and then that whole thing squared. So hopefully you can see we're just going to replace that XL minus XC for this number here, because that number there is the same as XL minus XC. So the next stage, again, we just say that Z is equal to, put the numbers in, the square root of, the resistance in this circuit was 80 ohms, squared, must not forget to do that, plus, and then we're going to put in the value here that we calculated up here, so 4.19 squared. And again, what's interesting here is that if this had come out as a negative number, when you square a negative number, because you're doing a negative times a negative, it becomes a positive and just cancels out. So it wouldn't matter if you'd got those back to front. I don't think I wouldn't have docked you any points for that. But that's what we're looking at this stage. So now we put that into the calculator. Again, I always like my learners to kind of map every single stage of this out. So I'd get them to, you know, show what 80 squared was and 4.19 squared is. But in the exam, the marking criteria is showing it's acceptable to just jump straight into this bit. So let's put this into the calculator because it's quite nice. So we go the square root of 80 squared plus 4.19 squared, like that. Hit the equals button, and now we're coming out with 80.10965. Round it off to 2 decimal places because that's the highest level of accuracy we've got here. 80.10, but the number after the 0 is a 9, so that 0 goes up to the next number, so that becomes 80.11. So the impedance of this circuit is equal to 80.11 ohms, and there's your next mark. You getting tired yet? Okay, so the next and final step, we're nearly there. Okay, so you've done very well if you've hung on to the end of this video, so thank you for sticking with me for this long, it's much appreciated. So let's have a look now at our final calculation, which is to find the current. Okay, so we want to find the current. This is actually what the question's been asking us to find. Now to do that, here's our final mark that we're going to get from this question for 5 marks. I is equal to, now normally when we do Ohm's law, we think of it as I equals V over R, okay? But what we're going to do here is we're going to just modify it ever so slightly and say I is equal to V over Z instead, okay? So we've just replaced the R with the Z because Z is also a type of opposition to current flow. It's the total opposition to current flow in a circuit, it's the impedance. And so we can just swap that R out for that Z, which is lovely. So if we say I equals V over Z, then we're going to put in here I equals, remember earlier we said that the voltage is 230 volts. So we're going to put that in. 230 divided by Z, the impedance, and Z, the impedance, I'm struggling to remember where we found stuff, it's here, 80.11 ohms. 80.11. Okay, so then we put that into the calculator. So we've got 230 divided by 80.11, nice and easy. And you can see there we've come out with 2.87. 2.87. And that is 2.87 rounded to 2 decimal places amperes. So the answer to this question to calculate the total current for this circuit is 2.87 amperes. There's your 5 marks for that question. So there we go, that's the answer to question 6 in the level 3 8202 exam from April 2022. If you're watching this as a way of getting prepared for your next exam, that's a very good idea. Hopefully this will be helpful, but it's a real challenging question. It's one that takes quite a bit of time to work out. As I say, I don't know how long this video is now, it's probably somewhere around the 15-20 minute mark or something. But in the exam, in reality, it doesn't take anywhere near that long because you're not explaining every step that you're doing. You're just working your way through that formula, that list of formulae. But it's a challenging one. It's a tough question. So if you manage to get through your exam in March, or when was it, April 2022, then you did really, really well if you managed to get that one right, because that's a really tricky question, so well done. Very good. Please hit the like button, make sure you subscribed and hit the bell to turn your notifications on so you'll get all the latest content, and stay tuned for the next question in this series where we work through the Science and Principles questions in that exam. Again, if you'd like to buy me a coffee or a tea because it's cheaper, then please click the link in the description. But again, there's absolutely no pressure to do so, and all that remains in this video is to say thank you very much for watching.